Allow me to welcome to the stage our next presenter. I've had the pleasure of working with Revathi for a number of years now during not only our time at Berlin Care, but also her very brief time at VI Grade, in which she left a very marked impression on a number of our customers. Revathi's now with HBK and their test services group, and in a recent collaboration with BASF created a really unique way of assessing engine mounts. So I'd like to welcome to the stage Ms. Revathi Rengarajan.
Good afternoon, everybody. Welcome to this presentation. As Gary said, this is what I'm going to be presenting today is based on a study we did with BASF. So thank you, Ricardo and Chris. I know Chris is here today. And this is based on their work with composite materials. And specifically for this study, we wanted to assess the NV performance of their composite powertrain brackets, specifically for an EV application. And I want to highlight through this presentation all the ways an NVH simulator model became extremely important in these evaluations and evaluating the results in the right context. So I'll quickly go through the motivation for this study and then some of the technical approach and instrumentation test considerations, and then I'll jump into a little bit of the results themselves. Okay, as a lot of the speakers before me spoke about, a lot of the themes in today's industry is lightweighting, cost savings, and that's exactly one of the big motivations here for this particular study. As you're aware, lightweighting affects a lot of different aspects, everything from fuel efficiency, reducing emissions, and with EVs, getting improved range. And in this domain or aspect, composite materials are becoming a trendsetter and an important aspect that people are interested in studying, how you could use composites to really assist in lightweighting. And a lot of materials like BASF's ultimate glass fiber reinforced composites, we're told based on the application can provide up to a 50% cost reduction, which lightweighting and cost reduction sounds great. So that quickly became the motivation for the study. How can we understand how these composites fare in a electrified powertrain, but also, or specifically for powertrain mounts? So we went ahead and we did a study to evaluate the performance, but we didn't want to just focus on a component level study, but we wanted to be able to evaluate it in situ in the vehicle. And I've been using this word a lot today through all of the demonstrations, but in the right context. Often you have silos, or when you're testing just your components and you don't quite understand how they fit into the greater soundscape of a vehicle. And a tool like the NVH simulator is a fantastic way to bring all these different pieces together into context. So what I'll show in the next couple of slides is the approach we took for a study like this, what tools and methodologies we used, not just, again, to evaluate this objectively, but subjectively as well. So not just squiggly lines on a plot or, oh, that's 3 dB better. What does that really mean? How does it affect the actual experience of a driver sitting in the vehicle and experiencing it along with everything else? And then the third piece I want to demonstrate, and this was an add-on slide to the study that we did, is once you have a model like this, I want to demonstrate how powerful it can be in expanding your study and doing other things. So if we started out with a test-based model, how can we add other components, simulation, and do several what-if studies without moving away from that seat that you're in, without actually going and having to make this part of a actual vehicle? A lot of decisions can be made, and I want to demonstrate a quick example here today. And I'll say this up front, we have some of these models and examples set up on our desktop simulator here today, so if anybody's interested in coming through and listening to some of this, you're welcome to stop by. Okay, so jumping into the technical approach here. For this study, what we did was based on a test-based approach, but I think this opens up a model like this, again, opens up a lot of avenues of other kinds of data that come into play. But for this study, we focused on using a source path contribution or a transfer path analysis study. So this is bread and butter, typical for NVH deep dive troubleshooting and target setting type of studies. So we use this to quantify the NVH performance of these mounts and understand their contributions in cabin. And then we took the results from this and put it into an NVH simulator for the subjective experience to be able to evaluate this back to back between like the baseline mount and what their mount sounds like, and then add the right context as well with that. I think a couple of speakers who spoke before me did touch upon using a source path contribution approach or a TPA approach, so I'll try to be brief with it. The concept here is that you're trying to quantify or characterize all of the possible acoustic and vibration sources of your system or the system of interest. So if you're interested in powertrain noise and vibration, you want to characterize all of the possible acoustic and vibration sources and then characterize or sum all of them up together to say these are the different pieces that make up the total sound that you experience in the vehicle. Now, in a test-based approach, you achieve this by putting a large number of transducers, both microphones and accelerometers around your source of interest, and then you do operational studies, and you do static artificial excitation type studies, and then you combine the results. You feed all of this into an SPC model, and it will give you all of the pieces. It'll tell you what each of the different sources, what are the partial contributions from each of these sources as experienced at the receiver level. So if you have quantified everything correctly, the sum of all of those contributions should add up and be the same as if you put a mic at the receiver ear and you measured that, they should all make sense. That's the goal, and that's the foundation of the study or the model that we built here. So great. What comes out of this type of a model is, these are my top contributions. Is this an airborne or a structure-borne problem? Does this particular motor mount that I actually care about, does it make it to the top of the list? You're starting to answer a lot of questions, which in the context of the vehicle are very important. You're no longer just isolated to the little, just one component, but you're starting to understand how it matters in the greater scheme of things. And so you take a model like that, and when you migrate it over into an NVH simulator model, you now have opened up many more doors and opportunities to do a lot of other things. You can take one subsystem and have a very detailed SPC model, but now I want context. I want to see how road noise and all the other sounds of a vehicle come together. Then this is a great way to do that. You can have different TPA models, and you can pull all of them together into the simulator. Again, something that was, these were all, I feel like every bullet point I have on here was something that one of the other speakers gave as an example or an actual thing they've incorporated in their study or in their workflow today. So you start to combine all of these things, and then you have now a model that it's virtual, but it's drivable. It's the same. It's pretty much comparable to going and hopping in a vehicle and driving, but now you have so many more possibilities at your disposal. So jury studies, target setting, target cascading, evaluating design changes, all of this become possible. So for this study, again, it was a test-based approach, so there are certain things we took into consideration for the SPC study. This was a powertrain-only study, and all of our transducers that were used to characterize our sources were all placed on the subframe or body side. This is a pretty standard practice. This helps make the test approach a little bit easier. You don't have to deal with any kind of rubber isolation that you have if you were to place transducers on the active side. And so it's easy to then go do your static test with an impact hammer, which is a reasonably easy approach. And then the other piece to it is for the SPC process, we use a matrix inversion approach, which is again a pretty common approach. And here there are certain rule of thumbs to remember. In order for the maths to work out, you need to have the right number of redundant transducers that will help identify or quantify your sources and the associated source strengths. So our typical rule of thumb is you want over, or at least 2 indicators per source. And the advantage of this approach also is that because all of the instrumentation is on the subframe or body side, if I'm doing mount swaps, I only have to measure one set of transfer functions. I only have to repeat the operational study when I swap the mounts in a test approach. From a sensitivity measurement standpoint, again, we use artificial excitation, so in the form of impact hammer test for structure-borne and volume velocity sources for airborne. Again, mostly standard things that come with the SPC technique. The thing I want to highlight is because this is an electrified powertrain approach, the thing to remember is frequency ranges. You're probably good if you just went up to 1600 hertz with an IC engine from a structure-borne standpoint, and then you go higher for airborne. But then with an EV, you need to expand both your structure-borne frequency range that you may care about, as well as the airborne. Airborne content now goes to much higher because you have inverters and higher motor RPM operational ranges to consider. And then operationally, in this case, we did everything on a chassis dyno. You can replace this with, I want to do a test bench approach to get my powertrain contributions. That's an option. You can substitute in different sources from where all of these pieces come in. But in our case, this was all on a chassis dyno. We did different operating conditions that will help build our model. And like I said, this was the piece that was repeated for both the mounts. Okay, I'll talk a little bit about results. I think this is the thing I really want to highlight. We started with just the component level. We had an accelerometer on the mount itself, and we're looking at some results by doing a static test. And it looks like, right off the bat, looking at those 2 plots, the dotted black curve has a lot more, it's a lot more elevated in response, and then you have a lot more peaks, whereas the traditional mount is pretty flat below 800 and above 1200 hertz. So there's maybe some indication that this may not maybe meet like a natural frequency design criteria you may have, or there might be possibility for deterioration at the source. But then, is this really the full picture? We still don't know yet how much this component matters in the total soundscape of the vehicle. So we got to dig a little bit deeper. So the next step was to look more at the operational data, still at the receiver ear. And typical powertrain application, you'd look at significant firing orders if it was an ICE. In this case, we identified motor and gear mesh orders, certain motor and gear mesh orders to be of importance, but then when we compared those, there wasn't really much variation. Maybe the gear mesh orders degraded a little bit, but then not really a lot to comment on. So we looked at broader frequency bands. If you look in the color map, you can see, 900 to 1500 hertz is maybe looks worse in the bottom plot. Again, 2000 to 4500 hertz looks worse, but this data was collected on a dyno. So you got to consider the fact that we're still not accounting for realistic masking content that would be present in an actual vehicle. So that's the real takeaway here. It looks bad, but is it really bad? And the added piece that the SPC analysis gave for us is to establish, okay, is this a rear motor problem or not? And we found that this was rear motor dominant. We found that the airborne and structure-borne pieces associated with that mount that we cared about had an impact, or was a significant enough contribution that we would care about it. But again, we still haven't evaluated it in the right context. And so what we did is we took this data and we took all the order content out of it, and we need to replace all of the dyno noise, which is the masking from the measured data, with more real data. So we took operational road and wind noise that we could simply plug in. It's just a one line item element in this model. And when we evaluated it that way, those results look line on line. So it basically suggests we have no degradation in the performance in the context of the entire vehicle, with the right vehicle, with the right kind of isolation and masking content that vehicle provides, you don't see a difference. This was both objectively, and when we listened to it, you really couldn't tell the difference. Even when we listened to the orders by themselves back to back, you really couldn't tell the difference. And this is pretty important, the fact that now you have an option where, from an NV standpoint, you've confirmed that there's no degradation in performance, but then you can now get a significant weight saving. That's a big win. And of course, you want to meet all other performance targets, but then the NV checkbox seems pretty good. I will skip over this one, but I will do another example here. So that was the main part of the study where we focused on a lot of those structure-borne contributions. But another important piece that I threw on here for this particular presentation is, we have this model now. What else can you do with it? And this is a great example. We got some data from ESI Group, where they did, for the airborne piece of it, think of it as an example study that they did, and we were able to adapt it pretty quickly and easily to this particular model that we built. So they did a motor encapsulation simulation study, and they basically used their NVH software and gave us results in the form of a filter, which compares, which is basically a ratio of the sound power with encapsulation and without encapsulation. And we were very easily able to plug it into our model and quickly evaluate, oh, if I applied this to all of my airborne contributions, what would it sound like? And if you were to do something like this in a test-based approach, it's going to be a lot more effort to really encapsulate the motor really well and be able to achieve similar or same results very easily or quickly. I want to play this video real quickly because that'll help. And so the model that I show up here, it has, like I mentioned, we added the road and wind masking, and then we have all of the different groups, which are broken down based on orders related to motors and gear mesh orders and so on. So I threw on this filter that I showed to a bunch of the airborne groups on there, and then we'll basically experience what it sounds like with and without the filter. You can tell pretty quickly the effect of that encapsulation. It's pretty obvious, and this is the simulation that was done was for a realistic scenario, so we're not over amplifying the encapsulation or the result of encapsulation. This is a pretty realistic scenario that we've taken and applied to this particular application. Again, just another example of how once you have a model like this, you can start to do a lot of those what-if studies and connect a lot of the dots. And this is also a great example where, and Vinod mentioned it in his presentation, but once suppliers and OEMs start talking in the language of simulation simulators, then it's easy to connect all of the dots, get all of the context, and get everybody talking the same language. So I think there's a lot of value in the outcome that we got from this particular study. So yeah, in conclusion, this was a great study to highlight the advantages of using these type of composite materials, which gives you a lot of mass and cost savings without really affecting NV performance. And for this particular EV case, we proved through a pretty deep dive study using an SPC and NVH simulator models that yes, you have to assess the risks and opportunities here and these type of tools give you the right context to do everything. And finally, again, we were able to do other what-if studies once you have a model like this. And I'll stop there. I'm way over time here.
No problem. All right. So look, Revathi will be floating around a little bit for questions if you'd like to ask her. But Revathi, before you leave the stage, I just have one question. You presented this at SAE NVH, correct? And you did win a Best Presenter award for that, correct? Thank you very much. All right. Revathi Rengarajan.